Okay, so here we have to find the volume inside the cone z is equal square root of x squared plus y squared, and inside the sphere x squared plus y squared plus z squared is equal to 1. And we should do the problem in both spherical and cylindrical coordinates. Of course, we should get the same answer uh, using both approaches. Okay, so first let us start by sketching the figure or the solid whose volume we want to find. So the sphere of radius 1, and then have a cone like that. And so I'm looking at this one. Of course, in a previous exercise, we identified that the cone has equation phi is equal pi over 4. So in spherical, let's do this in spherical first, where x is rho sine phi cos theta, y is rho sine phi sine theta, and z is rho cos phi, where of course phi belongs to 0 pi and theta belongs to 0 to pi, and rho is positive. Okay, we have seen before that this cone z is equal to square root is equivalent to phi is equal pi over 4. Finding the volume of the solid, let's call this region R, wants to integrate 1 dv. Now, rho will vary from 0 to 1. I could do this. Phi will vary from 0 to pi over 4. And theta will vary from 0 to 2 pi. Of course, we have the Jacobian, rho squared sine phi, d rho, d phi, d theta. It's easy to see that this is 2 pi times 1 minus root 2 over 2 times 1/3. Now, in spherical coordinates, we have seen this, we have evaluated, or we have described this region in terms of spherical coordinates. Now let's describe it in terms of cylindrical coordinates. Now recall that cylindrical coordinates consist of x is equal to r cos theta, y is r sine theta, and z, which is equal to z. Okay, so in cylindrical coordinates, first we have to describe really, notice that z is positive here, right? Like we're integrating where z is positive. In the region of integration, z is positive. So z will be equal to square root of 1 minus x squared minus y squared, since z is positive in this case. And in fact, z will be less or equal than square root of 1 minus x squared minus y squared, and bigger or equal than x squared plus y squared. So in terms of r, you know that x squared plus y squared is equal to r squared. And this is r. Great. Now I figured out z, where z ranges. I technically need to look at the intersection of the cone and the sphere. So intersection of cone and sphere. What do we notice here? I mean, we could replace z by r, and this is r squared plus z squared is equal to 1. Of course, here r is positive. What is that? then we get the 2z squared. So here, replacing z by r, we get the 2z squared is equal to 1, and z is equal to 1 over root 2, since z is equal to r is positive in this case. Great, right? We're looking at a positive region in z. And hence, x squared plus y squared will be equal to 1 minus r squared will be equal to 1/2. So really, the curve of intersection of these two is a circle whose radius squared is 1/2 at the plane z is equal to 1 over root 2. This is the circle here, the circle. Now, I project the circle onto the xy plane and I consider the interior. In fact, this is the region where the sphere is higher than the cone. And I get that I have to integrate over the region or over the disk of radius 1 over root 2 in the xy plane. So really r will go from 0 to 1 over root 2. You know, in the xy plane, this is x squared plus y squared is less or equal to 1/2. And theta will go from 0 to 2 pi. So what we have to do now, consider this in spherical coordinates. Theta will go from 0 to 2 pi. R will go from 0 to 1 over root 2. Z will go from r here to square root 1 minus r squared. dz, dr, d theta. And of course, I should not forget the Jacobian, which is r. This is not too bad to integrate. So what do we get? I mean, we can eliminate the theta immediately and get a 2 pi, but let's not do that. So what do we get here? We get, of course, when I integrate with respect to z, r is constant. This is nice. So of course, this doesn't depend on theta, and I'm integrating over a rectangle, so it's 2 pi here. Now let's find the antiderivative of this. You can do a u sub, but you can still check that you will get this minus from r equal 1 over root 2 to 0 minus r cubed over 3 from 1 to 0. Let's compute this. This is just 2 pi minus here, you know, the 2 will cancel out, so you get 1 minus 1/2. So you get 1/2 to the 3/2 over 3 plus 1 over 3 when r is 0 minus 1/3. Oops, we made a mistake somewhere. Let's double check that. Root 1 minus r squared minus r. Oops, sorry, this is 1 over root 2 here, right? So this is 1 over root 2 cube over 3. This is 2 pi. So this is just 1 over root 2 cubed. So these two numbers are actually equal. So it's 2 times 1/2 to the 3/2 over 3 plus 1 over 3. And this is also minus 1/2 to the 3/2 over 3. And you know, you can simplify that. This is 1 over 3. So you can write this as 2 times 1/2 times 1/2 to the 1/2 over 3. And then minus 1/2. 1/2 to the 1/2 over 3. So you get 2 pi 1 over 3 minus 2 over root 2 over 3 minus 1/2 times 1 over root 2 over 3. I mean, let's see what answer we got there. Let's try to get this. So what do we get? Yeah, so you get 1 over 3. Bring this together. Oops, here it's, no, that's good here. Minus 2 minus 1/2, so this is minus 5/2 root 2 over 3. So it's 2 pi 1. So multiply by root 2 on top, so you get 5 root 2 over 4. Oops, there's a mistake somewhere. Let's double check. 1 over root 2, sure, that should be good. One over root 2 cubed, yeah. That should be fine. Plus 1 over 3, that's good. Minus 1 over root 2 cubed over 3. So, I mean, we could do this way. Oh, okay, yeah, I see the mistake. Should have removed this. Yeah, okay. Right, I just added these two and I forgot to remove it. Okay, so let's just factor this out. And indeed, we get the same answer here and here.